Next up, we're going to do an example that uses that convolution property, the integral property that we first wrote at the start of these videos. And so we're going to be trying to compute et sine, forgot the convolution sign, et star sine t, where star is that convolution operation integrating 0 to t, f of tau, g of t minus tau. So I just want you to see what convolution is in one example. So following the definition, if I want to compute e to t convolution sine t, I'm going to take integral from 0 to t, and then I'm going to switch my first function to be in terms of tau. So e to t becomes tau. And then I want to switch my second function, which is that sine t, to be in terms of t minus tau. So everywhere I see t, I'm going to switch it for t minus tau. So in this case, it's going to be sine of t minus tau. And then we integrate all that with respect to tau. If I had like sine of 2 times t, I would make sure to distribute the 2 across the entire t minus tau, but in this case it's a little bit simpler. So I'm just going to go ahead and tell you that this is an integral that you can take, I think, by parts. I can't remember, but I wrote down the answer for you at some point, and it's right here. When you evaluate this integral with respect to tau, you get e to tau sine of t minus tau plus e to tau cosine of t minus tau. Times a half, if I didn't say that out loud. And then you evaluate it from 0 to t. And remember, because we integrated with respect to tau, these bounds are values for tau. So when I finish out one of these convolution integrals, I'm always going to be substituting back in for my taus. This is usually the place where mistakes are made. So let's go ahead and try that. I'm going to plug in t first, so e to tau becomes e to t. Sine of t minus tau becomes t minus t. E to t again, and then cosine of t minus tau becomes t minus t. That's my upper bound. And then I subtract and plug in 0. So e to tau becomes e to 0. Sine of t minus tau becomes t minus 0. Again, e to 0, and then cosine of t minus 0. I'm going to move that all over so I can put my last square bracket down. And then I'm just going to simplify this. So t minus t is 0. Sorry. And then e to 0 is 1. And there's just one more step to make this a little bit simpler, which is noting that at 0, sorry everyone, at 0, sine is 0 and cosine is 1, so that first term goes away, and I'm just left with e to t times 1 from this cosine 0 type term. And then my sine t and cosine t stay the way they are. And that's how you compute a convolution integral. So something to be really careful about is that tau should go away after convolution. So once you've evaluated the entire integral and plugged in those definite bounds, there should be no taus left over. If you find tau in your answer, it means something went wrong. And another thing is that you should just be careful about when to apply the properties we learned about convolution. So specifically this L of f star g equal to f of s g of s. We're going to have some examples where we use this in the forward direction, but normally we won't. I'm going to switch slides to show that to you in a second, so slowing down to give you some time to pause if you need it. But if we're asked to go ahead and compute L of e, just put in those convolution symbols anywhere, e to t star sine t. We're going to note that by the property, this is L of e to t times L of sine t, which is really easy to do. It's just 1 over s minus 1 for the e to t, s minus a, and then for sine t, k is 1, so it's just 1 over s squared plus 1 squared is 1. So when you apply L of f star g equals f times g in that direction, it's very simple. But if instead you said, okay, L of e to t star sine t is, compute this whole convolution integral that took us quite a while to do, L of 1/2 e to t minus sine t minus cosine t, and then went ahead and computed all of those Laplace transforms and moved forward, you would get to the same place eventually, but it would be much more difficult. So in general, do not compute a convolution integral unless you need to. And I'll go ahead and write out that rule. We don't want to compute f star g to plug into a Laplace transform. Instead, we're just going to use this forward property. Or the product of those two functions. And really the only time f star g evaluation is going to come up is when we're undoing that kind of product. So the only time you expect to compute f star g is when you're taking inverse Laplace transform. L inverse of a product would give you a convolution that needs to be calculated. So that's the convolution example and a little bit about convolution. Oops. And I went ahead and moved forward even to telling you when to use it. So I'm going to go ahead and pause here and get started on the next set of videos, which is going to be an example that we actually use that inverse Laplace transform.